In this module, we'll describe two pairwise interchange-based heuristics for the linear assignment problem. Note that this module is based on the INSY 3010 course, and we use material that we've gone over in class from there. So when I make reference to things that were done in class or things that were done in previous videos, it will be that set of videos that I'm talking about. So for our assignment problem, we assume that we have a cost matrix that we see here, where cost Cij is the cost of person I doing task J. So again, if we pick C32, this represents the cost of person 3, let's go back, doing task 2. And so this is the basic structure of our problem, is that we're given this cost matrix, and our job is to assign exactly one task to each person and exactly one person to each task. And so we assume that our matrix, our cost matrix here, is square. In order to represent our problem, we use the data structures that we see here. So we have a cost matrix, cost ij, and the solution is stored in two different lists. People I is the index of the task assigned to person I, has a value of -1 if unassigned, and task j has the index of the person that task j is assigned to. So we have our solution represented two different ways with people and tasks. And so it's important to note that as we update these, if we make an assignment, we have to update both of our data structures. And so for our example problem, cost ij, which show up as this 3 by 3 matrix, when we initialize the problem, people, try that again, people would be equal to -1, -1, -1, and tasks would be equal to -1, -1, -1 also, indicating that none of the people are assigned tasks and none of the tasks are assigned to people. We've spent quite a lot of class time talking about these data structures, so if you're still unsure of how they work, make sure and go back and check your notes, because we're not going to focus on them anymore for this video. So what I'm interested in is a process called pairwise interchange. And pairwise interchange is an improvement process where I start with a given solution. So for example, you can see here that I have task 2 is assigned to person 0, task 0 is assigned to person 1, task 1 is assigned to person 2, and task 3 is assigned to person 3. And so in our solution representation, we can see we have people is equal to 2013, and we could do the same thing with tasks. So person 1 is assigned to task 0, person 2 is assigned to task 1, person 0 is assigned to task 2, and finally person 3 is assigned to task 3. And what we're interested in the general assignment problem is this total cost, the total assignment cost. So in this case, we have an assignment cost that we can get by just summing up all the individual assignment costs. So this solution has a cost of 185. So the idea of pairwise interchange says, I've got this solution. What if I pick two people and they exchange their tasks? So for this example, suppose that person 1 and person 2 swap tasks. And so in this case, person 1 will be doing this task, and person 2 will be doing that task. And so you can see that solution, the tasks 2 and task 3 aren't changed at all, and we simply have the swap in our people list, and then because it's 0 and 1 on the task, the 0 and 1st element of the task list also changes. And so the resulting cost that we see now is 126. And so the question is this a good swap? So recall that our objective here is to make the assignment that meets our constraints, and that each person has exactly one task, and each task is assigned to exactly one person, but our objective is to minimize the total cost. So since swapping person 1 and person 2 tasks resulted in a lower overall cost, we would say that this is a good swap that we would potentially want to make. Whether we do or don't make the swap depends on the specific heuristic that we're using based on pairwise interchange. But again, the whole idea of pairwise interchange is that I start with a solution, I pick two people, and I test to see whether that swap is good and try to figure out that impact of that swap on the total cost. Before we look at the two heuristics, let's just look at recomputing this improvement, or look at the cost of making the swap. As I mentioned before, when we swap the tasks of person 1 and 2 in this case, the other remaining tasks, in this case tasks 2 and 3, aren't affected in any way. As a result, the 84 and the 30, those two components of the cost function, remain the same. And so what we'd like to be able to do is figure out, is there a more computationally efficient way to compute the impact of doing a swap? So if we look at these in detail, you can see that there are 4 components to our cost change. Person 1 no longer does task 0, and that saved us $65. Person 1 now does task 1, and that cost us 8. So by making that swap for person 1, we in effect saved, what would that be, $53? Or 53 units, whatever that happens to be. Then the second 2 components deal with person 2. So now person 2 no longer does T1 because T1 is now done by person 1. Oops. And person 2 now does T0 and person 2 didn't do that. So we can compute that cost, the generic cost, using our cost matrix. Recall that our cost matrix is the cost of person I performing task J. And so our overall swap cost for 2 arbitrary tasks, I and J, is simply the cost associated with person I not doing their currently assigned task, plus the cost of person I doing the newly assigned task, J, minus the cost of person J not doing their currently assigned task, plus the cost of person J doing their newly assigned task. And so you'll note that these 4 components of the swap cost function correspond exactly to the 4 things that we saw in the example that we just walked through. And we can actually see the swap in our 2 assignments right here. So this is people I and people J. This is person I not doing its current task and now doing person J's task. And then we see the opposite right here. So the first method we're going to look at is called random pairs pairwise interchange. And it's a very straightforward process. What it basically says is start with a solution. Start with a solution. And then for I in range, oops, let me see if I can clean that up a little bit. For I in range, let's call this in reps. For I in range in reps, select a random pair, I and J, if swap cost of I and J is less than 0, in other words, if this results in a lower total cost, then I want to swap tasks I and J. And so you see, when we execute this, we will start with an initial solution because, as I said, this is an improvement heuristic, and so you have to start somewhere. And then we'll simply iterate through some, and nrep stands for number of replications. That's what nrep stands for. In this case, a replication corresponds to 1 pair that we're going to test. We simply pick a random pair. We see if it's an attractive swap, and if it is, we make it. And then at this point, we can simply print the assignment. Print the assignment. And we're finished. Okay, so let me get rid of this for a second. Get rid of these so we can draw on here. And let's look at, in this procedure, where's the actual work that we're doing? Well, we first have to decide the number of replications, but that's pretty easy. You just pick a big number. We can select a random pair. There are many ways to do it. If we're using Python, we can simply use the random sample range length people 2 function, which will then return to us a random sample of 2 people. Again, a sample of 2 people picked randomly from this range length people, which is simply the enumerated list of integer up to the number of people in the people list. Next, to compute the swap cost, we can simply implement the function that we just developed. So previously we developed this expression for the swap cost, so we can simply implement this as a function and then just return the value. So return this computed value. So we'd compute that to, oops, it keeps switching pages, sorry about that. So we would compute that to an actual variable and then return the value. And finally, the last thing we have to do is actually swap the tasks. And so looking back at our data structures, we have to update two components. We have to update the people list and the task list. So what I would do is set a temporary variable equal to people I, then assign people j to people I, then people I, I've got these backwards, sorry. Let me go back and fix this. So I would assign people I, people j, and then finally people j equals temp. So we're storing the in a temporary variable the current value of people I, then we're overriding the current value of people I with the value of people j, and then we're using that temporary variable so that we restore so that we can actually make the swap. Next we would do tasks. So we would do tasks people I is equal to I, and tasks people j is equal to j. Why does that thing keep switching? So we could simply create a function that does that makes the swap, create a function that does the random, that computes the swap cost, and then we have a very straightforward process that we could do the random pairwise interchange process. For the second heuristic, I won't make you look at my handwriting for this one. And this one's called Steepest Descent Pairwise Interchange. And the reason it's called Steepest Descent is what it tries to do is figure out what's the best swap and then do that one. So in the pairwise interchange, in the random pairs pairwise interchange, basically what we did is we checked a swap, and if it was attractive, we just immediately made it. Right? That's what's happening right here. This time what we're going to do is we're going to go through all of the task pairs and then find the best swap that exists among all pairs. So we'll start out this way. We'll create a list of all pairs of people. So for example, this is going to be a list of lists. So person 0 and person 1, person 0 and 2, person 0 and 3, all the way up to person n minus 1 and n. So there are a bunch of different ways I can get this. We'll come back to that in just a little bit, but let's just assume that we have that, and we call that all pairs. Then we need to store our incumbent solution. Min cost is 0, min I is -1, and min j is -1. And what we're going to do is we're going to figure out what the best swap is. We're going to assume that has a cost, or we're going to set that swap cost we're going to set min cost to that swap cost, and then set the corresponding indices. In other words, who did we swap, our I and j, using min I and min j. So we're going to do it by taking for pair in all pairs. So we're going to end up with, inside that for loop, we're going to end up with a pair that looks like that. So this will be pair is equal to, in this particular case, 0 and 1. And so that would be, let's look at the swap of person 0 and 1. So we would compute that swap cost right here using our swap cost function. And recall that we're trying to find the most attractive swap, so we're trying to find the most negative value, because swapping two things is attractive if it reduces the overall cost and the swap cost is negative. So if the cost of swapping the current two people is less than the min cost, then we update the incumbent solution. Update the incumbent solution. And we move on. Our next step is while cost is less than 0, because what we're trying to do is do the most negative value. So suppose we did all pairs and there was no attractive swap to do. In other words, all the swaps resulted in either a positive or 0 value, then min cost would never be updated. So we would never update the min cost temporary variable, and min cost would have a value of 0. Oops, this is supposed to be min here, right? Hold on a second. This is supposed to be min cost. And so if that min cost is less than 0, that means we found an attractive swap. And so what we do in our while is we then make that swap. So I'm then going to swap person I and person j from our current incumbent solution. So once I do that, I've made that swap, I'm then going to go back in and do the whole thing again. Because I made a swap, then all of our, some subset of our swap costs will also be updated. So I'm going to go back in and recompute. So this is finding the best swap. And I'm going to do that exact same thing right here inside my while loop. Right? And so I do that twice, entering my while loop to figure out whether I have any attractive swaps when I start, and then as I get through the update phase, to continue doing that. And so you see what's going to happen is we will check all pairs of swaps. If there's any attractive swap, we will make the best one. That happens right here. Then we will recompute all the swaps, and if there's any attractive swap, we will make the best one. And so this process, because we have the while cost is less than 0, this process will continue until there are no more attractive swaps. So let me go back and correct something I said earlier. When we were talking about finding the best swap here, I said we're going to do that twice, right? We do it once here, and then we have it again in the pseudocode here. What I actually meant is we do this at least one time to see if there are any good swaps. Then if there was at least one good swap, we do it at least a second time. But we're actually going to do this computation until we don't have any more good swaps. We don't actually know how many times I'm going to find the best swap. It's going to be an undetermined number. It will be determined by the specific data. Finally, clue as to how to get this. What we need here is all combinations of size 2, and I suggest you look in itertools in the Python library, and it provides a very simple function call that will return these values to you. So to summarize, in this video we looked at two different heuristics based on the notion of pairwise interchange for the linear assignment problem, where we sequentially looked at swapping the tasks assigned to individual people. In one heuristic, the random pairs procedure, we made a swap as soon as we determined it was attractive, and we continued that process for a fixed number of times, and that would be a large number. For the second one, we sequentially computed the best possible swap for the given solution, and then we updated the solution accordingly. So two different heuristics to solve the same problem. Of course, for this problem there are many more heuristics, and for most linear assignment problems this problem is actually quite easily solved optimally.